everyone. It's a pleasure to be here, and I'm really thrilled about this effort. And I'm delighted to be allowed to serve on the Scientific Advisory Board, and I'm also, of course, very happy to tell you a little bit about what we have learned so far working in this arena. My lab really, as Rebecca just mentioned, deals with chemical compound space. And so this is a concept which maybe is not commonly taught in high school and even at the university level. And so I'd like to explain you a little bit how we explore that and how we use machine learning methods and quantum mechanics to explore that space. So let me start by this statement, which maybe many of you know from Dirac, basically saying that all the fundamental laws are known and chemistry is solved. That is, of course, quite a statement, but he then qualifies it saying that we only have to solve these equations, right? And that's the problem with the statement, that we need to solve something like a Schrödinger equation, which is a differential equation, and it consumes vast compute amounts to do that. But in principle, it's true. And so what people then did over the years is to develop a hierarchy of approximations, really. And this hierarchy allows us to navigate this space of chemical compounds at different levels of theory. And so these are force field, semi-empirical methods, mean field methods, explicitly correlated methods. And you see that their accuracy improves, but it's not a free lunch. You have to pay for that with the compute time you're willing to invest. And so if you come up with good approximations, with improvements like Walter Kohn did or John Popel, so Walter Kohn popularized density functional theory, which on average is sort of gets you more for the same amount of compute. You get a better accuracy. Then they were awarded the Nobel Prize for this work. So in my lab, we try to tackle this problem using two approaches, and they are shown here. One of them relies on perturbation theory, which is really an old and a well-established method from quantum mechanics, and the other one is based on machine learning. And so basically, this is founded on the fact that we have correlations which we can exploit, right? While here in perturbation theory, we basically construct derivatives and Taylor expansions. And so this is a little bit the picture then. We have correlation versus extrapolation, or correlation versus deductive derivative-based methods. And so I think this of them rather is complementary sides. It's a little bit not that dramatic, but let me just very briefly tell you that there are correlations and that there are relations across chemical compound space. And this is something we could show using these perturbations. So if you look at the molecule N2, this is how its electron density looks like. And these are the first four derivatives of the density as you change N2 into CO or BF, right? So this is also shown here. This is how the energy changes. And you can see we can smoothly extrapolate here. And using these derivatives, we can estimate the electron densities of other molecules. So the quantum information of one compound contains the information already of other compounds, right? And so this is known from perturbation theory, but it hasn't been exploited much yet. But this can basically make you confident that there are relationships among compounds, right? And we ought to be rigorously able to exploit those also within statistical methods. Now, we are quite excited about this because we also recently discovered a symmetry relationship in this compound space, which until now we think it hasn't been really discussed yet. So we dubbed this the alchemical chirality. And you can see it quite easily. If you consider benzene, you could perturb it to a molecule like this, BN-doped benzene, or you dope it twice and you get something like this, right? So this would be the benzene density, and then the first order derivative looks like this. This is the perturbing potential. And there's the expression for how the energy changes with respect to the benzene molecule. And this is just a Taylor expansion due to Hellman-Feynman theorem. And so we can construct another molecule which looks like the opposite. It's like a complementary compound, right? But any chemist will tell you these two molecules are not the same, right? These are constitutional isomers. Now, this Taylor expansion shows you, however, that these derivatives are exactly the same except for the sign. And so if you calculate the energy difference between these two, you find that they will cancel exactly up to third order. And then the higher order terms have alternating sign. But we understand this very well. And so there's this mirror image in nuclear charge in the composition space, which exists. And so if you look at the perturbed densities to a higher order, you will see they virtually look alike. And so there are these relationships, really. That's what I'm trying to tell you. Right? And so we can use this, for instance, to estimate a bond energy between nitrogen and carbon by expressing it in terms of energies between boron and carbon and two nitrogen and boron bonds. And so these are like constraints in compound space, right? They restrict where you can move, and you can exploit these symmetries to reduce the necessary data, for instance, to exploit these correlations statistically. So you can generalize this in the periodic table, and that's something we are very excited about, and that's something we are pursuing. But this also works in 3 dimensions. It's not restricted to benzene. You see here in the lattice of diamond, these two compounds, right? They carry the same or approximately the same electronic energy. But I'd like to tell you now about how we make use of these correlations using machine learning. And so there is, on the same plot of error versus cost, right, of accuracy versus cost, you can ask this question, okay, can we train a machine learning model that gets better? And it gets better now, not with the cost of the compute, but rather with the number of training examples, right? And so this is really for us the paradigm shift in quantum mechanics. You can add more examples, and the model you have trained, which you can then apply to new cases, right? This model becomes increasingly and systematically better, right? And it's a bit also frustrating because it's stupid. You just add more examples. You haven't really learned anything. It's just that your data density grows, and hence the interpolation improves. But it does so rigorously and systematically, and it was proven by Wapnick and others that the leading error term for out-of-sample predictions decays inversely with training set size. This was shown for kernel methods as well as neural networks, so it's a very generic thing you can show. But this really means that on a log-log scale of your error versus training set size, you ought to observe such a linear decay in your prediction error. And so then when you make your prediction for new compounds, a single prediction is blazing fast, right? So you get really here the advantage of this approach. So this previously this would have been very difficult to accomplish, right? This is what Walter Kohn got us, right? And now we basically can go here, and this is the paradigm shift as it presents itself to us. So we've been working in this field for quite a number of years now, and here are some reviews. The latest review was in Chemical Review. There was an entire issue devoted to machine learning chemistry. The way we think about it is really that in chemical space, you can represent compounds by linear combinations of other compounds, right? And so you don't always have to study each compound independently. You don't have to start from scratch for every compound. So there is an inherently multi-scale nature to chemical compound space. And that's what I still wanted to tell you a little bit about now. There is not a multi-scale nature in the sense of space, as we just heard about it from Rebecca, but also there is a multi-scale nature in terms of energies. This is something which we've been studying more or less implicitly in the past, and now more recently we explicitly included this kind of figure in a paper which is about to submit it. It's already as a preprint available online. The notion is that we really have composition, constitution, and conformation. Right? And these are, as indicated a little bit by these thermometers, right? They live on different energy barriers, right? If you want to go from one to the other. Of course, we can change composition, right, by replacing compounds. We can change constitutions by performing chemical reactions, and we change conformers when we sample, right? When we sample phase space, right? And so these are all regimes which we would like to understand and cover and control in order to truly freely explore chemical compound space. Now, the composition is, of course, something we all know from the periodic table, right? So Mendeleev's table, and this recently because it was 150 years in the New Yorker, it got an article which is quite rare for the sciences to have to be discussed in the New Yorker. So that's a gem. But have you known that there are different ways to plot the periodic table, right? And they are not wrong, right? This is another way. This Emerson helix. These are all ways to present the same information. And they encode possibly more useful information. Here, even more alternatives, right? So quite compelling. Now, you know this from basic chemistry that the pKa, the acidity of a functional group, will vary as you change other parts in the molecule, right? And we learn that if you go from something more electrophilic to something more nucleophilic, the pKa will exhibit a certain trend, right? But there are more examples like this. Another one I like very much is the Pettifer scale. So Pettifer introduced a new ordering scheme, and if you follow this line, what you find is that for carbides and nitrides, also other compounds, as a function of the order of elements according to this line, the formation energy of these materials, which is an incredibly difficult property, if you think about it from quantum mechanics and statistical mechanics, this property becomes linear in this line, right? So it's extremely powerful. You can directly read off, if you wish to have a certain formation energy, you just read it off, right? Which compound it would exhibit in, right? So it's trivially invertible, right? And so the design problem, finding the right compound that exhibits the properties you would like to, is for such cases it's close to trivial, thanks to reordering of the periodic table, right? So this was introduced in the 80s, but more recently Hardy Gross and Michael Marcus also revisited this, so there's still active research going on in this direction. Another example, which I actually discussed also in 2013, is this question of having multiple atoms. How should they, which atoms should they be made of, right? Which nuclei, which elements. And here you see a recent example from the literature where you see in a binary cluster, AN, BM, you see M and N, and you see certain islands of stability. This is an enthalpy of stability. And you find that for such a diagonal line, this could be an isoprotonic line with a constant number of total protons. And this was a paper which was also just published 3 years ago by Artem Oganov. In chemistry, there's something known as the Hamid relationship. It's a linear relationship of properties in compound space, and compound space is sort of mapped onto what's known as a sigma parameter. And you see the functional groups of the LUMO or the HOMO eigenvalue, they are the same on this scale, right? And so these properties, which seemingly are not obviously related to each other, they map onto the same sigma axis in compound space, right? And so this is something we recently revisited with large data sets. We improved on the Hamid equation. So in this work, this the blue dots here. If you did Hamid the old way, you got worse predictive power. And we could also demonstrate the use of this for combining this with machine learning models. So here you see such a learning curve where the error drops as the training set is increased. And if we combine Hamid with machine learning, you see in green, this delta machine learning, you have the lowest learning curve. This means the most data efficient model, which required the least data to get where you wanted to. Coming to this question of constitution. How do you get from one to another? You have to do chemical reactions. And this is, of course, a gigantic space again. Right? So you don't only have elements, you also have the ways to connect them. And this basically graph enumeration problem, which is known to scale terribly poorly. And so this is what you would have in chemistry. This is an example of constitutional isomers. They all belong to the sum formula of C7O2H10. If you plot their enthalpy, all these organic molecules, in ascending order, the energy looks like this. And in this inset here, you just see the results for roughly 100 molecules. And you will notice the enthalpy falls within 1 kcal per mole. So there's 100 molecules, different distinct molecules that have an enthalpy of formation within 1 kcal per mole window. And this is the experimental uncertainty in thermochemistry combustion experiments. Right? So from experiment, we couldn't distinguish them. Yet they are very different. So there's this richness of chemical space. It's very dense. But by contrast, if you go down here, there's only one molecule at the end. And after that, there's nothing. Right? So you have chemical space can be very dense, and it can be very scarce as well, depending on which energy scale you're looking at or where your properties are. So we wanted to look at this with machine learning, and we looked at a classic textbook example, 2 competing reactions. So you have a reactant here, 1. It can react either through an elimination to a double bond or through a substitution by replacing X by Y. Okay, and so this was the question: can we learn this in chemical space as we vary the substituents R1, R2, R3, and 4? And we also wondered, can we answer then what is more frequent in chemical space? Is it E2 or SN2? I'd like to take a quiz now. Everybody hands up who thinks that SN2 is more frequent than E2. 1. So everybody assumes E2 is more frequent than SN2. And you're right, I will show you. This is actually true. So we prepared and used a data set for this study that contained a lot of reactions. And we started, so this is how the data looked like. These are distributions of activation energies. And this is how the statistics of the transition states geometries looked like. And then we trained machine learning models. And you see them up here. For the SN2 and for the E2 reaction, using only the reactant as the input, right? So the machine learning model would either predict one barrier, or for the other barrier we would use a different machine learning model. And then we used these models to make the prediction of all possible reactants. And what we found is shown here. So this is the difference in activation energy between the two mechanisms. And if this is positive, you have an SN2, and if this is negative, you have an E2. And so we find roughly that 3/4 of all reactions are E2. Now, these are new things. We don't really know yet why it should be like this. It's not clear if this is in general true for all of organic chemistry, or if this also happens in solvents, and so on. But for this chemical space, this is the statistics you can find with this. You can then also analyze with these models certain structural features to see if they meet a postulate known in organic chemistry as the Hamid's postulate, which basically relates the proximity in structure between reactant and activated state. This proximity is correlated with the height of the barrier, according to this postulate. We confirm this postulate for SN2. You see a good correlation of these two variables. And for E2, there's a breakdown of this postulate. So these empirical chemical rules can also sometimes be confirmed or sometimes being devalidated. And now coming to this last part of predicting structures and reactions. So you might have heard of the Levantas Paradox. This is a paradox about the number of possible conformers. It's gigantic. And so this is the problem then of a chemical compound space. So you have an explosion on the composition scale, you have an explosion on the constitution scale, and on the conformational scale you also have an explosion. Right? And so we wanted to look at this if we can actually train machine learning models to predict the actual coordinates of a conformation. And so this is a problem which traditionally would require you to relax the geometry. So you would start out with some initial guess where you put the atoms somewhere reasonably, and then you follow the energy to minimize the energy function. We collected a data set, again, on these molecules with this stoichiometry here. And we use this data set of energies and coordinates to train a model. And this model basically predicts the interatomic distances between all atoms in your molecule that would correspond to the minimum geometry, the relaxed geometry. And we can then try to predict these elements in this distance matrix using the molecular information of the graph as an input only. And so in training, you need, of course, to have the coordinates to train. But then when you come to the prediction, you only need the graph as the input, and you directly get the 3D coordinates as the output. And so here in this first learning curve, you see for this data set, for these molecules, you see that we can systematically reduce the error in the coordinates of the structure. You see here some histograms of distances between predicted structures and reference structures, and then we also applied the same to other data sets to see if this really holds, and also for other stoichiometries, for radicals, for transition states from the data set I just discussed before. You see learning curves that all improve with structure, and even for crystals, you see that the geometrical features improve with training set size. So with this, I told you now about a paper with the Hamid equation. I told you about the reactions, and I told you about the structure predictions which we could make using machine learning. And with this, I'm coming towards the end of my talk. I told you about these learning curves, right? So the prediction error decays with training set size. This is very important. If you have a certain budget in terms of training set size, you might wonder, how can I improve my machine learning model so it improves? If you have a certain target accuracy, the same question applies. How do you improve it such that you hit the target? I think conceptually what we are witnessing is a little bit the addition of a fourth pillar in science. We had the experiment, we had our physics-based theories like quantum mechanics and statistical mechanics. We make use of simulation to solve these equations, and now we have statistical surrogate models that help us to accelerate, to infer the solutions of our problems. The community is very interesting, I think. It's very much an open source community. There are models and source code freely available. Data is mostly open access. Even workflows are published. So there's a lot of access here. And all of this has triggered us last year to actually start a startup ourselves. It's called LLIE. It should be live if you want to try it. You can enter any molecule you wish, and it should spit out a structure. Then you can also look for different properties of your molecule, or you can also contribute your own model if you happen to have one. So it's meant a little bit as a platform also, that people can share their models. And here you see an example of such a model that was not from us. So this is a solvation energy model from the Greens group and at MIT, where you see the free energy of solvation of cholesterol now predicted online through a web interface instantly. More recently, LLIE also added as an option cloud computing, and so we are trying a little bit to get a hold into this market. It was also mentioned I'm the editor-in-chief of Machine Learning, Science and Technology. There's a new journal from the Institute of Physics which tries to accommodate all sorts of contributions which have a link to physics, but which come from specific domains and might be interesting to other domains as well. If you wish to follow me, I'm also active on Twitter and YouTube. And finally, I should thank the people who actually did the work. So this Dominik Lem, Jan Weinreich, Guido von Rudorf, and Heini, Stefan Heinen here. I have to thank for funding the ERC, as well as Swiss funding sources and a research grant from Google. So with this, I'd be happy to take questions.